Hi all, I'm Flip Cromer from CSC. If you are if you are a large enterprise company and looking to get a big data solution done, working with your legacy systems, soup to nuts, vendor agnostic, we're who you should call. And I'm going to be talking about kind of exciting framework for understanding big data systems at scale. And so I'm going to introduce a couple things. So one is a set of patterns for architecture at scale, how to combine the different pieces to get a specific problem solved. And the other is a way to understand the trade-offs that we navigate when we're building high-scale systems. So kind of a more sophisticated version of the holy trinity, fast, good, cheap, choose any two. Let me introduce a couple examples so I can talk about what I mean by Lambda architecture, a term which Nathan Mars has popularized. So here's kind of a high-scale search solution. And what we have is we're going to build a global index in batch mode. This is going to be across every piece of text you've ever seen. This is large enough and the algorithms are sophisticated enough that you will also want to maintain a separate recent index for things that are just rolling in along the time. And then in both cases, you're going to serve them in immediate time from a fast serving layer. So you have a batch layer, a speed layer, and a serving layer that are respectively global, relevant, immediate. Another example, a recommender system, and pretty much every single machine learning algorithm. We have a batch process that builds your model, understands that, you know, the person who looks at skinny jeans and Honda motorcycle parts, you should recommend them a certain mustache wax. Then we have a live process. We're actually going to separate out application of the model. We're going to pull that out of the immediate layer into a separate layer, which is going to handle taking the page views as they come in live and updating the recommendation, right? So that, you know, hey, this person also looked at empire dresses. Let's instead recommend these knitting needles. And so that means that the immediate layer here no longer has all this fancy machine learning code in it. It's just doing, you know, O1 reads of the latest recommendation. So again, we see this batch layer operates globally. Speed layer, the speed layer, which handles relevance, and the serving layer, which is immediate, where the overriding concern is latency. And the technology for this should be familiar. It's basically, at the top is everything that's mature in big data. Your Hadoop, Spark, batch queries from databases. In the middle is all the stuff you have been hearing about, Hortonworks and Cloudera and the rest adding to their packages. Storm Trident, Spark Streaming, the SAMZA project, or even kind of older things like AMQP, RabbitMQ, et cetera. And then the serving layer is the stuff you use to serve it or the things you're using to display reports. So why is it called the Lambda architecture? Well, in my head, it's because if you look at the flow diagram, it has the shape of the character for Lambda. This, actually, the correct explanation is this kind of argument from Nathan Mars. He's the pioneer of Storm and writes wonderfully about how to think about data at scale. That what you want to do is reevaluate how we build data systems around the idea of a pure function on all data since the beginning of time. So what would that mean? What would an ideal data system look like? So I believe that an ideal data system would have exactly and all of these properties. It'd be able to operate on any amount of data, affordably and simply, without falling down. It'd be responsive, right? That any answer you want to serve out of the data system is returned immediately. It should be based on all the data you've ever seen, including recent data as it pours in. And it should be correct. It should be accurate and justified. And you would think that the stuff on the bottom was essential. Correctness, You'd think that that was the important thing. When you look at the trade-offs that we actually make, it's the stuff on the top. Those are non-negotiable, that you be able to afford it, that it be able to work on the data you must have. So that what we actually have to do is figure out where we are going to bend the truth with good taste so that we can maintain these properties on the top. Basically, it isn't fast, cheap, good, pick any two. It must be fast and cheap, relatively speaking. Do your best about being correct, truthful, relevant. Let's go look at more patterns. So I talked about the recommender pattern here, and I'm going to say that this is an example of what I'll call train and react. So in machine learning algorithms, you're going to build a model of the world, but this model changes slowly. So we can rebuild it at leisure, but what we have to relax is a little bit of recency there because the system underneath will drift. You know, the new fall collection rolls in, all of a sudden you have a bunch of things that are very poorly represented in your model of, given that people have bought this, what you should recommend. So we have to sacrifice recency because we're only updating the model occasionally. This usually is not a big deal because, like I said, the underlying world changes slowly. Now let me contrast that with the search and update use case. I'll say that this pattern we'll call baselines and deltas. You have an underlying, in this case, it's not that the world is changing slowly. It's that understanding the world takes a long time. You must have this batch process, which is extremely time-consuming. In fact, the world changes very quickly, and you care, right? Because you want to be able to have search on, trending topics, recent events as they unfold. So what do we have to give up? What we have to give up is simplicity in having this whole extra system lying around, and accuracy, which is, you can imagine that the speed layers algorithm is not going to be as sophisticated as the one applied in the batch layer. And for instance, it may be missing, normalizations as all of a sudden a whole bunch of text flows in around a certain topic. This same pattern, I showed you the search index where there's a live recent index and a deep historical index. You'd also see this when you're doing like if you were doing things like trending topics, heavy hitters, count distinct. A lot of approximate stream algorithms are like this. Let's talk about some graph examples that come up when you have graph algorithms. So here we're going to build some sort of reputation on top of social networks. Right? So it'll be, for instance, an example would be a PageRank. That let's say that these are users, and of course, for PageRank, you are interesting if interesting people follow you. So you have somebody where everybody follows them. You have somebody else where the most interesting people follow them. Those end up with heavy weights, and we have people in a backwater. Now, all of a sudden, a new user turns up. What are you going to do? Well, calculating the PageRank, it's, a piece, it's, in the first few chapters of your Hadoop book. But it takes a long time to calculate. You have to do it iteratively as batch jobs across the whole graph. So when a new record appears, what are you going to do? Well, what we'll do is tell a little white lie. We'll just update that one record as if they were there during the last, as if they walked in the room during the very last exchange of reputation of social capital. So that means that it's slightly inaccurate. We haven't actually included their contributions back to the rest of the graph. You know what? Planes aren't going to fall out of the sky because you got somebody's reputation slightly wrong until the time when you ran the next batch update, right? So that person on the left became slightly more interesting, but mostly we weren't too far off from the truth. So in a lot of graph algorithms, we're going to have this world and local situation where the relevant, where the speed layer is using local information to update, to keep the system relevant, and the global layer is ensuring the long-term justification. So clustering, whom to follow, anything that has second degree and built on a graph. The other thing I'll highlight here is that is when your set of trade-offs demands comprehensiveness. Like, it's not okay in this case to, when a query comes in about a user that you've seen, to say, right? I really like the Marine Corps rule of 80%, right? Any decision made with more than 80% of the necessary information is hesitation. So, and there's a lot of cases where you're perfectly willing to give up justification and accuracy in exchange for comprehensiveness and, of course, your must-haves, simplicity, that it be manageable and affordable on all the data that you need to do. In security, a problem that comes up very often is kind of, you have these two problems. So one is the Bradley-Manning problem. Why has a GS6 sitting at a console in Kuwait downloaded every single State Department memo over this long, difficult-to-detect period of time? And you also have this flash fire situation, which is, why is all of a sudden data streaming off of a whole bunch of our servers into insert country that you don't want your data going to here, right? So there's two wildly distinct tempos of data. One of them is too hard or not necessary to include data at full detail. And in one of them, it's too expensive to deal with all the data at once. So we're going to build into the fast layer kind of understanding of the rapid change. And into the slow layer, we're going to understand global and long-term effects. So trending topics is another example of this flash fire, slow boil kind of thing, right? So for trending topics, you're understanding this baseline of how often do people talk about Michael Jackson, and then the trending topics is, oh my gosh, everybody started talking about him, what's going on? So in banking, the basic problem there is absolutely overall, in the long term, it must asymptote to correct and not partitioned, right? But you also want to have availability. You also want the data. You want to be able to give and, most importantly, take people's money whenever you can. So transactions come in, and they're going to store atomically every single transaction, and they're going to do their best to update your bank balance. But, if they make a mistake, well, they make most of their money on fees anyway. What's most important is that the batch layer that gets everything correct be right. So in this case, the reason that you end up with the Lambda architecture looking thing is that you have consistency, availability, partitioning trade-offs, right? So that in your batch layer, you're going to, in the batch layer is going to ensure that all those bottom properties of true, correct, right, accurate, justified, recent, et cetera, that all of those are justified, while your relevant layer lets you still have responsiveness and comprehensiveness, that it's acting on all the data, including recent data, right? Not responsiveness, recency. So a common theme here is that we have the system asymptoting to the truth over time. That basically now that keeping around these two very different looking pieces of infrastructure, a batch layer and a speed layer, are both, that the operational expense of having both of those is much less than it used to be, that what we can do is kind of understand and in much more fine-grained fashion adjust how we end up with a system that ultimately is viewed as true as a function across all data. So those were kind of familiar patterns of data at scale. But I want to, there's one more here, which is going to be a entity resolution system, right? So we're going to scrape all the products off the web, and we have scrapers hitting, the individual vendors who have feeds, individual vendors who push data to you, individual vendors who upload, batch inventory, and then scrapers which are going and pulling data off of sites adversarially and friendly, and et cetera. And so what we want to end up with is a unified index where, this site is sending in its own version of the name of this product, and this one is sending in its own vendor code, right? This one's sending in the ISBN, and this one's sending in the, Amazon ID of the book. And so you're building these unified models. Think about like all the different ISBNs for different versions of what you might regard as one product where the variants are the different editions. And so you have these scrapers that yield partial records, and you're going to have a batch process which is going to connect all the different records to common identifiers that are going to unify all the ISBNs based on the very fuzzy matching of the title. That's difficult and has to be done globally so that you can detect titles that are almost the same but reflect different, let's say, books, or titles that are identical and represent the identical, titles that are slightly different because they're, two versions of the book or part 2 of the book or whatever. And then the resolver is going to use those unifier records to prepare a single product with all the information you've seen there. And so what you want to do is think about your system as what you should always look to do with these is see how to build the same process into the fast layer as you do into the batch layer. So if what you do is you think of the resolver as generically something that takes your best guess and one or many new facts and produces your new best guess, right? Now, in the batch layer, what that looks like is your best guess is the null prior, right? Maybe it's the empty model, maybe it's the average recommendation, whatever it is, right? And then what you're going to do is incorporate everything you've ever seen that attaches to that model in order to produce your best possible guess. In the speed layer, what you're going to do is usually have one or a couple where, you hit on identifiers that you could unify, scrapers rolled in at the same time, right? You're usually going to have a model that you've prepared in the batch layer, and now you're just tacking on new information. But you might ignore when a new fact showed up showing that this record over here and this record over here, oh boy. And we're back. When this record over here and this record over here were actually the same. And so this isn't so much of a pattern of when you're led into a Lambda architecture kind of thing as a good thing to strive for when building a Lambda architecture system. Now I want to argue that, so let's take the patterns and recap where we've gotten to. So I'd say that the Lambda architecture, which kind of from the outside can look like the self-evident, hey, there's a batch layer, hey, Storm is useful, and so is Hadoop, but you still have to serve data out of Tomcat or Rails or whatever, that it's actually about something kind of much deeper than that. You have fine-grained control over all of those architectural trade-offs. You're using these kind of similar systems that cover different areas of solution space to better get what you want, that ultimate ideal data system with all those properties. And of course, the enabling technology here is DevOps. It's the fact that you're better off with distinct systems that segment your concerns, right? You're better off with one system that prepares the model, and one system that applies the model, and then one dumb system that just serves up O1 pieces of pre-calculated data than you are trying to combine everything into a single system reading from a master centralized database. The other piece of it, and I think this is super interesting, is that the truth lives at the edges and not at the middle. That you have data which is syndicated forward into databases which then kind of are static, rather than something which is kind of the traditional data architecture, where you have centralized databases that are assemble your own answer at read time. Right? So you're doing your queries at write time, not read time. And I want to argue that this is actually, these are patterns for building scalable systems. Right? The way you solve your high-scale problem is to build a system that is scalable. And so, excuse me, and so that this actually continues to apply even at much smaller scales. So let's take the smallest scale I can think of, which will be a dinky little blog. If any of you have ever seen, there's the author of Rails, David Hennemeyer Hansen. He has this 5-minute video where he uses Rails from a dead nothing to build a serviceable dinky little blog with articles, authors, and comments in a 5-minute YouTube video, okay? And this follows the conventional way of doing this is to use your database as an ORM, that you have models, and at read time, you go query those models, and you return views, right? So your models are gonna be articles, authors of articles, and people and comments, by people. You use those at read time to prepare these views, and you can see that on here that there are fragments, right? Things pulled from the article model, things pulled from the associated user model, things pulled from the comments models. And this is done at read time traditionally, pulled from the database at read time. Another way to do this, though, that would be much more in keeping with the Lambda architecture philosophy, is instead, we're going to have changes come in. A new article was published or an update to an article happened. A new user signed up or a user changed their biography. And we're going to have a layer of what I'll call biographers. These are either listening for updates coming in, or they are on a timer going out to going out to external data sources, or their batch uploads, or whatever it is. These are things that are faithful to an individual source and are simply reporting new atomic facts that, in principle, you keep forever. And the biographers are responsible for updating what we'll continue to call the models, although there might, in this case, be more of them. They're usually faithful to the source, so they're going to look a lot more like the sources times the number of incoming models. Then you have separately a second layer of reporters, and reporters are faithful to a story. Right? Biographers are faithful to a source. Reporters are faithful to a story. So reporters are going to be tied to these view fragments. That there's going to be a reporter which updates, which invalidates the view fragment for an author's bio, so that when this page is reassembled, that when the page is assembled from views, everybody sees that updated bio without having to mess up the cache for everything else. So our reporters are going to go through and update only the view fragments that come out of any given change to only its inputs. What does this change? So remember, we're just pulling off of what we can do is now version each of these view fragments. So all of a sudden, you're not making changes to monolithic things, right? That the people pulling from the front end really just say, here are the records I'd like to retrieve, and then you version your API, and so that when they change their mind about what the target domain should have to be, that all it is you're adding another, there's no reason to throw out the old reporter until you get bored with it. And so you just kind of update it. Basically, a whole bunch of meetings go away because because people need to understand smaller and smaller parts of the system. The data's always there, just sometimes it's more perfect than other times. And this, I think, is the kind of most important thing about the Lambda architecture. It's this asymptoting the truth over time. That leads to things being decoupled. That leads to things being accessible in O1 time. But mostly what that leads to is radical decoupling among your teams. And that is actually, I am kind of crazy ahead of time, I believe. What should I go back to? Or do you guys have questions? How many people here are actually applying, are using things like Storm or Spark streaming in conjunction with Hadoop? Got some hands on the back. And so what are you using it for? Come on, yeah. And what happens in the speed layer and the batch layer? Okay, well, so the story there was that they're taking in sensor data in the speed layer, right? And then the batch layer is handling, is basically doing analysis across all of those, right? So I'd say this very much fits this is gonna fit that flash fire, slow boil pattern where right, so where you have data at two wildly different tempos that you're trying to analyze, and probably some of the baselines and deltas.
So basically what we are trying to do is give some context to the events, the incoming events in the speed layer. So based on the historical data, we are giving the context to each event, and we respond back to client actions, or let's say predict what the clients will go on doing, the next action.
Cool. Other questions or applications?
How do you cope within this architecture of component governance, so capability governance, for example, in terms of each of those components that you're discussing, what their role is and context is within the Lambda architecture?
So, sorry.
So, for example, the Lambda architecture can consist of a number of capabilities. Those capabilities would be Hadoop components, for example. So how do you support the governance and control of how those components are being used and how they conform to how they should be used going forward?
Okay, so basically, I think one of the big things here is that with DevOps, you're able to really, I guess one of our rules is if you can decouple, do, right? So I'm going to need you to tell me whether this answers your question, but one thing I see people who are adopting these architectures at scale are kind of too afraid to do is really to have a whole lot of architecture running around. That we find that what you really want to do is have separate deployments for each of your concerns. So you don't have a storm layer as your fast layer. You have storm layers for each of, you have kind of individual deployments for each of the things that you're trying to do. You're better off running lots of different architectures than lots of different deployments obviously all of them governed by DevOps so that the configurations are standard, than you are to have things tightly coupled where they have to fail and succeed together. That makes governance, right, access control a lot easier. The other thing that happens is when you have these kind of, I think one of the biggest things that changes when you are syndicating data forward is that it becomes a lot easier to do fine-grained security and to make that kind of, to have high-level, excuse me, to have policy live at your orchestration level. Let me just pull up any random system diagram. That you can apply policy rules at the, let me pull up the PageRank 1, right? So that you can have things that are down here tagged as PII. These are individually identifying user records. And then you can have processes that aggregate things enough that they would scrub the PII property from them. So that at the high level, you can make a statement that, like, personally identifying information should not cross these barriers. And then you have certain processes which are blessed as being able to remove the personally identifying attribute from individual records. Was that anything like what you were asking about?
Yes, I think it's twofold. I think there's how you use the component and how it's exploited is one part of it. The other part of it is how that fits into the existing IT architecture landscape and how it conforms with all the IT governance that you've got in place at the moment becomes very important. So it does answer the process side. I think the IT governance side is a far different area, and it will probably be different for every single organization out there because they have different processes in the IT governance. But understanding the concept of how splitting, separating out your concerns is a good way of doing it, and having standard configuration management is the right way going forward, really.
Cool. And this doesn't depend on having, kind of your latest newfangled, like, this architecture, well, look, the traditional way of doing it is Hadoop and Storm or Spark streaming, Spark and Hadoop and Storm or Spark streaming. But it makes just as much sense if your batch layer is, batch Oracle reports and your speed layer is RabbitMQ or SOA, RPC chains. It still makes just as much sense. Any other questions? Any other interesting applications where you'd say that you're applying the Lambda architecture? Cool. Well, next door is a talk on, next door is there's a question. Sorry.
How does the Lambda architecture affect like data science teams who are back testing models on that slow tempo on all the data and then forward releasing those to run in real time?
Yeah, well, I think, let me make sure I've highlighted well something that's happening in here. The traditional place with the recommender system that the model gets applied, that traditionally the model gets applied at request time as part of assembling the page. Look, it's kind of nice if you can say, people who looked at these genes also bought this sweater. That's a nice to have, and we know that that improves conversion and drives revenue, and of course it's because users actually wanted to see that other product. But what's really important is that you show them the checkout button, right? Like nothing can get in the way of that. And so if you have decoupled out into a completely separate concern, the thing that is preparing the recommendations so that at page generation time, all you're doing is reading out the best guess as to what to recommend the user. And if there's nothing in there, you're just reading out the Bayesian prior for what the generic user would want to have, then your site becomes a lot more robust. And life becomes a lot easier for the data science team because now they are free to iterate much more quickly, that they can just have a bunch of these different systems, right? They can have the next best, greatest thing, have that also writing into the database, and then start doing A/B testing of both of those at some certain fraction. These things become radically cheaper and easier to do. Was that helpful? Yeah. Cool. Any other questions? All right, well, thank you very much. There's a talk on Storm next door, or downstairs, so we can check that out.